Our next presentation is going to be given to us by Andreas Kortenhaus, who's a professor of coastal engineering at Braunschweig University in Germany. Andreas.
Thank you, Jonathan. Good morning. Well, first of all, I'm sorry. Well, if you expected Timo Schwekendick to present now, this is wrong. I'm sorry. We have shifted the presentations. We are running a little late by that. Yeah, you see, this is a long title. It's long because it's a 3 years project or 3.5 years project, and if you want to compress everything in one title, it's getting a little longer. Sorry for that. Second thing is, you see that the first author here is Marie Naulin. She is not here. She is not coming, so she asked me to present this for her. It's the old message saying, "Don't shoot the messenger." I'm only the messenger today. But I'm happy to get your questions at the end. Actually, I was quite heavily involved in that study, so at the end of the whole story, you may shoot me. Okay, so I'm trying to skip through the whole presentation rather quickly, and at the end of the whole, I would like to come with some open questions, maybe to trigger some discussions here. So what is the contents? First, a brief introduction to the whole thing, the methodology which we applied, the application to our pilot sites, some results, and the summary and the outlook. Well, motivation is quite clear. In Germany, we always have a reference back to 1962, where the big flooding of Hamburg occurred with over 300 casualties here, but it's still in the mind of people not only living in Hamburg, but it is one of our triggering events for taking a case study or pilot site in Hamburg. One of the methodologies back to the flood site project coming from that is the fourth pathway receptor. You might have heard yesterday's presentations on the sources. You might have seen presentations on the receptor side. This is now on the pathway. We nicely split all XtremRisK presentations where all this is coming from all over the conference, with the last presentation tomorrow afternoon then. This is a joint project coming from 4 different partners and a lot of external partners around it. It's more or less ending now, so it's a perfect timing for presenting all these results. You find papers and extra work on our website or in the CD in the abstract book. Case studies of pilot sites were Hamburg, as I mentioned before, and only specific areas in Hamburg, which is the area of Wilhelmsburg, which back in 1962 was heavily flooded. And the other area, so Hamburg is an estuary, 100 kilometers from the sea. It's a major city, as you may know. And in opposite, we selected Sylt Island, which is an open sea, sandy island in the north of Germany. Well, as I said, the overall objectives in the pathway, in the pathway sub-project we have here, is to look for, doing the probability of failure for the flood defenses which we find in the pilot sites. We have a nice link to the previous talk, because I'm happy you see all the background approach of reliability analysis in there. On top of that, we did some breaching analysis of dikes and dunes. And as a result, we're taking an input from our risk sources, sub-projects. All of these were scenario approaches. So we started everything with storm surges as a scenario input in terms of water level and waves. We then calculated the probability of failures of the flood defenses, and we did a breach analysis of the breaches which we thought occur, and gave a certain volume of water entering into the floodplain as a starting point for all the inundation modeling, which was the next step within the whole procedure. So the methodology, briefly mentioned before. First thing, you're looking to all elements in your flood defense, which in the case of Hamburg and in the case of Sylt is, a lot of the flood defenses which we are aware of. So starting from typical dikes or levees, going over to dunes, mobile walls, flat walls, storm surge barrier, you have the full variety. We then looking to failure mechanisms of each of these elements in the flood defenses. So simple things like wave overtopping overflow. We were going back to the analysis done in the flood site project, and we tried to expand it a little bit. Well, you've seen these slides before, uncertainty analysis, and with the uncertainty analysis we're doing a reliability analysis of all the failure modes which we assign to the different elements. And last step then is fault tree analysis to come up with the overall probability of flooding or failure at the end. That's the example of a fault tree, or a selection of a kind of, well, part picture of a fault tree for a dike. We're using up to 22 limit state equations for that fault tree for the dike, and we're using about 5 limit stations for the dune then to come up with the overall probability of failure. Top of that, we had a couple of breach models which we applied. Well, they are triggered either by wave overtopping from the landward side of the dike, or they're triggered by some wave impacts from the sea side of the dike and then go to breaching. And for dunes, especially for the sandy island of Sylt, we're using the Unibest and XBeach models to calculate erosion. Well, in looking to some of the results, the reliability analysis for this selected area in Hamburg, for Hamburg-Wilhelmsburg, first of all looks like that, and that's a point which I discuss later on as well, saying first thing you have to do, well, try to split all your flood defenses in different sections, because they are all different. They are using different elements, they're having different lengths, they are built of different materials. In Wilhelmsburg, this leads, well, the whole flood defense length is about 24 kilometers. So we came up with about more than 80 different sections, which we said are more or less consistent or homogeneous in itself. Of course, this is not true, but this is an assumption well, a workaround, if you like. And then at the end, after doing all these calculations, done through all this reliability analysis, coming to the fault tree, you come up with a probability of flooding or failure for each of these sections, assuming a certain scenario, as I said at the beginning. While we are all starting, we're all doing this for certain scenarios. And that gives up, well, you're coming up with, well, some simple values at the end, something in between 0 and 1. And actually 1 is a case here, because we have selected some very extreme storm surges where the water level at the end is higher than the flood defenses. So logically, you come up with a flooding probability of 1 in the case of that specific storm surge. What was that? Wrong button. Okay, sorry. Dike breaching, the same. Well, the simple assumption here is whenever you have a probability of failure for a breach to occur, then you apply a numerical model for dike breaching. And this model over the duration of the storm surge will give you the volume of water entering into the floodplain. Right? That's one of the assumptions in applying the breach models. On the other hand, as I said before, some of the wave overtopping and the overflow was so big because the water level was so high that you already have a lot of water entering into this area, assuming that there is no breach. So that's two assumptions which we considered, well, independently from each other. Anyway, these models seem to run quite well. We did some calibration with very little, well, data which we got from the field, from some very old analysis, and that gave us, first of all, the location, where does the breach happen, and second of that, how much water over time flows into the area. In case of Sylt Island, this is the southern end of the island. We're looking to the western side here on the left, which is all dunes. We did all these numerical analysis, and we came up with some probabilities of failures for this area for specific storm surges again. Again, this is triggered by scenarios. you see here that the probability of failure is a little, well, if you look to that in more detail, and it would have given you more time to actually look to that, then you see that the probability of failure in these cases is a little lower. We think that the scenario well, getting flooding from the western side of the island in the area of Sylt is almost non-existent. Well, wonderful. These things shouldn't show up at all anyway. Well, that's an example of some of the numerical calculations from the erosion models. One of the profiles I've pointed to the west side of the island of Sylt, a typical erosion during a storm surge. And in summary, how much time is left?
You're fine. You're perfect.
Yeah, well, this summary is not the end of the whole story. So I wanted. This is why I'm asking.
You're at 11 minutes.
Okay. Wonderful. So overall, we did this analysis, and I'm summarizing the dikes and the dunes, saying we're coming to the fault tree approach at the end, 22 limit state equations for dikes and 5 for dunes. We got all these numerical models for breaching, for dune erosions, and we applied that to the 2 pilot sites, coming up with some flooding probabilities, which was the first part of the risk analysis which we performed. And giving some further information in about times and well, the volume of water flowing into the floodplain, which then was taken up as the next sub-project to do the inundation modeling and the damage analysis. What is actually missing? And that's a more important point for me now. In many of these analyses, well, going back to limit state equations, we see that most of the limit, many of the limit, not most, but many of the limit state equations are, well, static in a way. They are not time dependent. And think of a storm surge coming up. Well, it's usually a rise of water level, it's a constant level, more or less constant over a certain time, and it's going down again. So the water level is very decisive, for example, in terms of wave overtopping. So why do we not consider that? If you're looking to the limit state equation for wave overtopping, then you're just comparing 2 values, the volume of water flowing over a dike or levee compared as to the admissible volume. This is a problem, we think. So it should be, sorry, I was too fast. This is a problem because I think we should consider times here, and that would be give us a much more accurate value of the probability of flooding in terms of, well, triggered by wave overtopping, as an example. So that goes to the next point, right? So we need to change that. We need to come to time-dependent variability or limit state functions. Second point. One of the assumptions we always take is we're restricting ourselves to certain sections within the overall flood defense line. The selection of sections, we have done an approach saying each of these sections is homogeneous. Of course we are not. I know there's another approach saying we're taking equal lengths of these sections and we do a correlation in between these sections. Both of which have a problem because we don't know, I would say we know something about it, but not enough to actually do proper values for these correlations. And another point we were always asked, so if you're doing an analysis or if you apply your numerical models for breaching, where do we actually apply it and how many breaches do we actually get for a storm surge? What does it mean if you have a probability of a breach of 0.8? Does it actually breach during this specific event? And if it breaches at this point, how many other points will have a breach? And how much water flows actually into the floodplain? For me, this is not entirely solved. And then, well, a couple of structures are still missing. They might be point structures, so there's only one point in the line, but they might be very important for the overall flooding probability. What happens if in Hamburg a gate remains open? Well, of course, this shouldn't be the case, but we're doing a lot of analysis in looking to our soil structures, but that could be very decisive, and it's completely ignored. Okay, I have examples, but I think I'm receiving signs that I should better stop now. Right, okay, thank you very much.
Do you want to leave that previous slide?
Yes, I do.
Thank you very much. Andreas, thank you very much. I think, well, certainly from my perspective, that slide very well summarises the issues we are also tackling in the UK as well. So, is that we have time for one question?
Sorry, I'm available longer, so we can discuss later.
Yes. Well, all the each failure mechanism will contribute to the total probability, but each limit state function has common terms, right? So when you analyze these probabilities, do you model everything at the same time? Like you calculate everything at the same time? Because if you consider the correlation of parameters, then the probability will be higher.
Yeah, that's right. What we do is, because that was a scenario approach, we took the same input parameters for all these limit state equations. That's a very simplistic way, if you like, to consider the dependencies of these input parameters. But that's the approach which we used. Because they are, well, default tree assumes that all these limit states are independent. And of course we know they are not, because they have the same input parameters. So that is what we've done, at least as a simplistic approach. We took the same input parameters and then calculated it by a Monte Carlo simulation.
Okay, Andreas, thank you very much. Appreciate your input.